Verstanden. Yeah. Oh, yeah. And go to the show. Shit. Zoom words. Yeah. Shit. Yeah. So. Small. And see what's going on. It's stream. Is that is somewhere? John. Yes.
Okay, all right. 1, 2, 3. Test Zoom channel. 1, 2, 3. alright การสดิตที่ OBS นะครับไม่ทราบว่าเสียงไปหรือเปล่านะครับการสดิตถ้าไปก็ตอบผมนิดนึงนะครับเพราะว่าเดี๋ยวอัดไปแล้วมันก็ใช้ไม่ได้ไม่มีเสียงครับ okay alright now let's continue our lecture alright okay yes we live at the device, right? A device that is used to measure the density of a liquid, right? Okay, actually the density of fluid, but we can say it's the density of a liquid, right? Okay, this one, right? We could also have another application. Okay, the hydrometer floats higher in a denser liquid, right? Than in less dense liquids. All right. ภาพใช้ได้นะครับ All right. Yes. Okay. In denser liquid, right? We would have a hydrometer floats higher, and oh no, it's not good at all. It is weighted at its bottom end so that the upright position is stable. All right. Scale in the top stem permits direct density readings. Okay, we just look at the scale here in on the bar here. Okay, inside the liquid tube. Okay, and that's the way we use to measure the density of fluid, right? It's quite straightforward. Okay, it's a mechanism style, right? Yeah, it's physical style. Human is quite clever, right? To apply this. Okay, ใครจะเข้าที่มีคนพิมพ์มาที่ซูมนะครับ2 คนนะครับมีปัทานินกับชัยศิลป์ครับ right so I don't understand why all right yes let's go ahead with this we have another application of the way to measure the density like this. Okay, just if you are quite close to your father or your family, right? Sometimes actually in the older technology, right? They use the battery, and the cars have the battery inside the hood, right? And you may notice that someday you cannot start your engine. And one of the reasons for this problem, for this issue, is that the battery doesn't have enough electricity. Okay, it doesn't have enough power to let the motor rotate so that it can turn the engine, right? So in order to start, right, when we don't have enough electricity or power in the machine, right? So in the battery, one of the reason is that we have to look for the condition, okay, to check what condition of the battery is. So yeah, in that own generation of the battery, they use the acid, right? In it's cheap, right? In this way, the technology, when you use the acid together with lead, like PB lead, you would have a cheap type of battery. And yes, you may notice how the condition of the acid is, and one way to see this is that you have to observe the density of this liquid, which is the acid, right? Acid. And the good battery would also provide an indicator to let the owner see how the condition of oh, sorry for that. I don't understand why there is another voice. There is another sound. Okay. Yes. Yeah. A good battery should have an indicator, and that indicator is made like this. Is like a ball, and the ball would stay in this area, right? If we have enough, we have good condition of the acid, the ball here would stay like this, right? And it means the battery is fully charged. It has full power for electricity for being used with other electric devices in the car, right? And once the battery is used for a long time, the condition is not good. The acid density may change with time, right? And when the density is not in this the appropriate level, is not so dense as before, this ball is gonna go down, okay, and stay like this, right? And yeah, when you look at this pipe, when you can see the ball here, it means that your battery is in a good condition. But when you look at the battery in this situation, you will not be able to see the ball at all, right? Because the ball just stay at the end of the tube here, right? We would be able to tell ourselves that now the battery is not in a good condition, okay? And you will replace the battery, or you repair this battery by changing the acid or in whatever technique, okay, in order to solve or fix this issue. Okay, and that's one of the application for the battery, or for the density in the battery in the automobile industry, right? Okay, we often say that an object placed in a fluid is boiled up by the fluid, right? Yeah, we are right at the buoyant force, right? And so we call this upward force the buoyant force, denoted by B. Okay, B is, let's forget the notation of B for magnetic flux density from the previous semester. Okay, B now is the used for the buoyant force. Okay, we use the first letter of this word, right? Buoyant force. It means the force that try to move or keep any object up, right? Take it up. And the average density of an object is what ultimately determines whether it floats or not, right? So one of the factors that the buoyant force depends on is the density of the liquid in or that object, right? Okay, yeah, it depends on the density of two things: the density of the object and the density of that fluid, right? Okay, let's take a look at figure 52. Okay, on page 117, we are considering a glass that is full of water, and you let a piece of an object get into this water, right? And yeah, in the first example on the left, if, okay, this is what we have in this experiment. In the first experiment, the density of the object, which means the black cubic here, okay, the density of this object is less than the density of the fluid. The fluid means the liquid here, okay, and yeah, if you try to put it at the middle of the cup like this, and when you lift your hand, okay, when the density of this one is less than the density of the liquid or the fluid here, yeah, you can observe that the buoyant force, okay, which is denoted by the letter B with the arrow on top. And of course, we have any mass should have its own weight, right? Because it stays on the planet, on any planet. And yes, this one is the weight of this object. Let's say, okay, it's yeah, M and T, right? The vector of gravitational acceleration is going downward like this, according to the center of the Earth, right? And the buoyant force is the force that's trying to lift this material up, right? And in this case, you can see that when the object has less density than the fluid, the buoyant force is going to be larger than the weight, right? And yeah, this mass is going, this object is, yeah, according to the Newton's law, right? Sigma F equal ma, right? So the acceleration, okay, let me write down sigma F equals ma, right? And you have two forces acting right now on the object, downward force and the upward force. And in this case, because the fluid is more dense than the object, so we would have more buoyant force, okay, greater buoyant force than the weight of that object. So after we put two forces into the left-hand side of this equation, we would have the acceleration outcome as the upward direction like this, okay? And yeah, we would see that finally this object is going to move up, okay, and float on the surface of this liquid, okay? And that's the first experiment. Let's take a look at the second experiment when the density of the object is greater than the density of the fluid, right? In this case, of course, we have also the same amount of buoyant force. You can see the length here of vector B are the same on both figures, right? On both figures, we have the same length of the buoyant force. Let's say these two objects have the same volume, right? We have a single volume for these two masses, two objects, but the density of the silver box here, silver cubic here, is greater than the one on the left, which may be wood, right? This is a kind of metal. And of course, with the same volume, you have more, when you have, with the same volume, when you have more density, you would have also more mass, right? Because rho is m by v, okay? If you have the same volume and when you have more density, it means your mass is going to be greater than that, right? Your mass is going to increase, right? So when we observe again the weight, right? W is going to be m times c, right? That's the weight. Now the weight is the magnitude of the weight is greater than the magnitude of the vector B, the buoyant force. Of course, when we put these two forces into the left-hand side of this equation, we would have the acceleration of that mass, okay? And now the vector is pointing down, okay? We get the the arrow pointing down like this. All right, and yeah, you would get the acceleration of this mass pointing downwards, right? And of course, you can guess that this object is going to move downward. Okay, it will not go in any other direction, right? Because the total force is pointing downward, so this object will move downward, right, to the bottom of this cup. Okay, and those are the two phenomena you could get from the nature, right? It depends on the density of the substance and the density of the fluid, right? Whether it's less than or greater than the density of the fluid, right? So let's move to the next page. Now, you have already seen the situation that could happen in nature. It depends on the density of both material and the fluid, the liquid, right? Now we are going to observe the qualitative detail of the buoyant force B here. Okay, let low F, okay, low with subscript F, be the density of the fluid. Okay, let's say the fluid here inside the glass has the density of low F, and rho O be the density of the object. Okay, let's say this material, the cubic here has the density denoted by the variable low O, right? And yeah, VO is the volume of the object, right? O stand for object, okay, the first letter of the word object. And the buoyant force can be computed by displaced fluid weight, okay? If you let the water surface or the liquid surface as same as the edge here of this cup, and when you bring the material here inside this liquid, right? The liquid is going to get out of this cup, right? And you just measure the whole amount of that of this exceeding liquid, right? And yeah, you need to you would be able to find the volume of that liquid, right? And yeah, the exceeding amount of the fluid, okay, out of the glass or out of the cup here is denoted by VO. Okay, we have VO and the density of that liquid, whether it's the liquid still inside the glass or the liquid out of the glass, okay, because both have the same density. So we have the low F, right, the density of fluids. And yeah, when you have also, we know that low and F, low and V, right, the density times the volume that is exceeded out of the cup is going to be equal to the mass, right? And the mass of the liquid that gets out of this glass or this cup times the acceleration will be equal to the weight of the exceeding fluid, okay? And the weight of the exceeding is exactly the same force that try to lift this material, this object up, okay? And that force is called buoyant force, okay? From what we have, from what I said, we can write this relation as the expression in 75, equation number 75. B buoyant force here, okay, the magnitude of vector B is equal to the low F, okay, which is the density of the fluid, and VO, the volume of that object, of that material. And G is the gravitational acceleration on Earth, okay? If you live in any planet, just use the gravitational acceleration of that planet. If you live on Earth, just use 9.81 or 9.8 or simply number 10. If you live in Mars, you live in Neptune or any planet, okay, just use the gravitational acceleration of that planet. Okay, yes, let's go ahead with that. The weight of the object is calculated from, simple, right? W is mg. M of what? M of this object, right? Not M of the fluid, because we are considering the weight of this object, right? So it's going to be rho O, VO, and G, right? So rho O is the density of the material, the object. And once you put both quantities into the left-hand side of the Newton's, I don't know, second law, right? Second law, you will get on the left-hand side, right? Let's say, according to the y-axis, if we have any vector pointing up, we would say it's a positive. If we have any vector pointing down, we would say that vector is negative, right? So buoyant force is pointing upward. We have the positive in front of B. The weight is pointing down, so we have the negative in front of the weight, okay? And yes, the buoyant force is low FVOT, right, from 75. And the weight of this object, sorry, I should open this. And the weight of this object is actually the weight of this object is actually the mg, right? Low VOG, right? So you could see that when you substitute 76 and 75 into the left-hand side of this equation, we get the right-hand side here. The common factors are going to be VO and G, right? Both right-hand side in these two equations have the same two things, right? The VO, which represents the object of that material, and the gravitational acceleration on Earth, right? We have we leave this one on the planet, right? When you move the common factors, VO and G, out of this difference, you get this one, right? And a totally submerged object that is denser than the fluid sinks, okay? Any object that's fully submerged into the liquid, it means that object has more density than the fluid, okay? And the net downward, we consider the situation when this material is going to move down, okay, move downward. We don't consider the steady state that where when this object already stay at the bottom of this glass, okay, we don't consider that. We consider the transition period when this object is going to move down. Okay, we get that expression like this. Okay, is the acceleration. Okay, we want to observe, okay, is pointing down. So anything that is pointing downward is going to be positive. It's the same thing. W is pointing down. We have W in front of B, and the acceleration is now low O minus low F. Okay, instead of 77. Because we are considering the acceleration of sink object, okay? So the net downward force is going to be this term. All right. Now let's take a look at the case when the object doesn't have the center of gravity point, okay? We don't have when the center of gravity is not at the center of that material or that object, okay? For example, we don't have we have a non-uniform material when this region is more dense than other part of this material, okay? I don't know, it's made from special material. This location has more mass than other part. So the center of gravity of this object is going to stay somewhere here, okay, not exactly at the same, not exactly at the center of this object, right? So the whole volume of this material would have the center mass, right? Center point of the whole structure right here, but the center of gravity of the object is right here because okay, it's not made with the uniform material. The density is not uniform in the whole piece of this material. So this one is heavier than the other part. So center of gravity lies here. And in this case, the fluid doesn't know which point is the center of gravity of that material. They would take a look at the whole volume of this material and they leave the it would leave the buoyant force at the center point of this material. Okay, they don't know this object has non-uniform material inside. So at the starting condition right here, you know that this object has the force pointing up in this way, and this object has the downward force right here. And of course, both points are not the same location, are not in the same location. There would be moment, right? And moment, and yeah, once it moves downwards, this object is going to rotate a little bit according to the force until these two forces are aligned in the same straight line. Okay, when both lines are exactly in the same alignment, okay, this object is going to stop movement or rotation. Okay, and that could happen also in nature. All right. Yes. Okay, you have already completed the whole theory about buoyant force. You just remember the formula of the buoyant force, right? And the mass, the weight of that object from this one, right? We have only these two equations, and we are gonna solve several examples later. All right. Yeah. Let's remember again that the buoyant force is the density of that fluid times the volume of this object times the gravitational acceleration on Earth, right? Yeah, a bargain hunter. Okay, a bargain hunter, it's the guy who deals with the business of gold and so on, right? He purchases the gold crown at a flea market. Okay, it's an unofficial market. You just walk and try to buy the cheap thing, right? You don't go to the gold shop because the price of the gold there is higher, but it has also better quality, right? Yeah, this guy just go to the flea market and he look for a gold or precious stuff, and he want to buy the precious stuff, and then he want to sell it in a higher price so that he can get benefit from that, right? Okay, he can get the difference price from that. Yeah. After it's not he, okay, it's not male, it's female. Okay, after she gets home, okay, she has bought a gold crown, okay, at a flea market, and she gets home. When she went home, she hung it from a scale and finds its weight to be 7.84. Okay, this is the location where there is it's flea market. Okay, she just walk around the street and she just picked up a cloud, okay, which she's supposed to made of gold, right? And then she returned home, okay, returned home here. And after that, she just hang the crown, okay, the crown here with a spring, right, which is a kind of the device to measure the weight, right? So this one is going to have the weight, right? Okay. She then weighs the crown while it is immersed in water. Unfortunately, she is not straightforward. She didn't use directly the typical weight measurement device, right? She leave this one inside a glass or container that has the liquid inside, right? And once she, I don't need to draw the figure at all because they have also provide the figure right here on in figure 54 on page 122, right? 122, okay. And yeah, that's the whole thing, whole story of this example, this question. As on the right side of figure 54, okay, she leave it 7.84, okay, in and also in the second situation, she leave it inside a liquid, which is again inside a container, and she found that the weight now becomes, the weight of this object now becomes 6.86, right? So the question is the crown made of pure gold? Okay, that's the question, because she needs to know whether this product is made of pure gold or not. Okay, if she find that this is the genuine gold, right? The gold is 100% pure inside the crown, so she would sell it in a shop with a good price, and when she get a good price, she get a benefit from this business, right? Okay, yeah, let's consider the two situations that she tried to observe. Okay, she just simply used the principle of the physics about buoyant force, right? She hung this crown, okay, which is supposed to be made of gold, and yes, the spring on the weight deliver the value to her as 7.84. Okay, in this case, okay, it reads 7.84 Newton. Okay, the unit of the force from the spring is Newton, and in this case, what she can read from the scale is 6.86 Newton, right? It's T. Let's say this is T2. Okay, the tension of the spring or on the rope or string here in the second situation. This is the first situation, and here is the second situation, and here is T1, right? T1 is 7.84, T2 is 6.86, right? And yeah, the different thing in both situations is that here we don't have any buoyant force at all because we don't leave the crown inside any liquid, right? So just simply in the air, right? And this one is different. We leave it inside a liquid, and yeah. The question is this crown is this crown made of pure gold or not, right? So what should we do then? How could we give the answer to this question, how could we tell whether this one is this crown is made of pure gold or not, right? Yeah, the way to deliver the answer is the following, right? Right. Yes, we you may notice that you may notice that you need to know the actual condition of this object, right? Because we are interested in whether this crown is made of pure gold or not. So we need to know the actual property of this crown, okay, or this of the gold, right? So you need to know first what is the density of the gold, right? In how? Okay, you should you should know first what is the density of the gold, right? So you need to look at the table about the density of the pure gold, right? We don't care about the contamination, the gold that is not pure, right? So this is viscosity. Okay, it's not the correct table, right? We are talking about the gold, right? Yeah, this is compressive strength, right? Where is that? This is bulk modulus. Right. All right. Where is the table of density? Surface tension. Right. Where is the density? Viscosity. Here. This is the story about density, right? Okay. Here we need to see what's the density of the gold, right? Because the element we are interested in is gold, right? So rho or d you can also use. Here the substance. Okay, that's the first column. Look for the gold. Gold is right here in this line, and the density of the pure gold is 19.3. Okay, that's the crucial value you need to know first. Okay. The density of pure gold is 19.3. Of course, the standard weight is kilogram per cubic meter. Okay, so you need to compare. Okay, compare the so the theoretical value or the desired value of the density of this crown should be the same value of the density of the gold, right? Because we want to prove whether this one is the pure gold or not, right? So yes, we have to look for, okay, whether law of gold equal the rho of the density of crown or not. Okay, let's check. Let's check whether this equality holds through or not. Okay, let's check whether this equality holds through or not in this situation, right? As we know already, rho gold is this one, 19.3. We need to determine the density of this crowd, right? So yes, yeah, let's determine, we need to find the density of the crowd, right? So the first step is that we have to find rho of the crowd, right? So density of the crowd, okay, and what is that, right? And in the second situation, you have to compare. Okay, compare the rho of crowd, the density of the crowd, to the density of the pure gold. Okay. Oh, sorry for that. Compare, right? So let's get into the detail of the first step, right? The first step, what is the density of the crowd, right? In this case, you can see here that they have already provided the detailed sketch or the force diagram of this experiment, the first experiment, right? Yes, of course, from the first law of the from the first Newton's law, you will see that when the objects stay constant like this, we have stay idle, you have sigma f equals 0, right? So this is the first Newton's law. And yeah, you would see that, let's say, along the y-axis, we have the positive thing, right? So the tension of the string, which is going to be equal to, okay, let me draw the stump so that you can better understand. You can completely understand, right? Now this is the crown, right? This is the crown. And you have here the string, the tension string, and you have the weight of that object pointing down, right? It's W, right? Which is mg actually, okay. And this one is the T, right? The tension of the rope or the string that try to move, bring the crowd up, but because this just stay in a constant situation, the force upward, the upward force and the downward force would be the same, right? So we would have a T equal W, right? But T in this case, let's say is T1 from the first experiment. They say that the tension which is observed by this weight measurement device is the 7.84, right? So it means the weight of this object, weight of the crowd. Okay, the weight of the crowd is 7.84 Newton. Okay, you get that value simply from the first experiment. Okay, this is the first experiment. Okay, you just get this value, the weight, which is mg. You can also find the weight, the mass of the crowd, right? If you want to find the mass of the crowd, of course, W crowd is going to be mass of the crowd. Oh no, this one, mass of the crowd times G, right? And if you want to find mass of the crowd, you just mass of the crowd is going to be the weight of the crowd divided by G, the gravitational acceleration on it, right? If you put it into the to into the calculator, you would get the weight. Oh, sorry for his mass of the crown. M instead of W. M, right? M crown will be 7.84 by 9.8. Okay, and leave it from the calculator, right? 784, right? 784. Mass crown, mass of the crown will be 7.84 in the next, oh, sorry. Divided by G, right? 9.8. Okay, and you get value of them 0.8. Okay, it's 0.8 kilogram, right? The mass of the crown. 0.8 kilogram. It's quite heavy. Okay, on the head. If you are the owner of this crown, if you want to wear it, it's almost 1 kilogram. Okay, it's like the laptop. Okay, no, it's like iPad. Okay, you carry iPad on your head. Okay, it's the same sense. 0.8 kilogram. Okay, from the first experiment, that's the mass of the crown. So now we already get the mass of the crown, right? But our destination, our target is raw crown, right? Please note that our target is the row of the crown, right? Row of the crown, the density of the crown is the mass of the crown, right? Divided by the volume of the crown, right? So right now, the mass of the crown is known already there, right? Which is this value here. Okay, it's known. The second one we need to know is the volume of the crown, okay, which is unknown and unknown. Oh, sorry. Unknown, and we need to find it. Okay. So now let's go ahead with the second experiment. We need to find the volume of the crown. How could we measure the volume of the crown? This lady is quite clever. She just leave it inside the liquid, okay, and see the difference, okay. And by using the physics principle, okay, let's get back to our story. The test of the crown, whether it's genius or not. Whether the crown is genius or not, right? So yes, in the second experiment, it's a little bit complicated, but it's not beyond our ability, right? We have the, let's draw the a force diagram to this object. It's an object here, it is a crown, right? But right now, once you have the second situation, second experiment, of course, according to what we have learned, there will be also the buoyant force, right? Buoyant force up. Okay. Of course, the first force is still the same, which is the tension. Okay, tension in the second situation, which is readable from the scale in the weight measurement device here. It's what is that? It's, as we know, it's 686, right? 6.8 6 Newton, okay, 6.86 Newton, and of course there will be the weight of this mass. This is the weight of the crown always, okay, all the time, whether you leave this mass in any location, okay, whether it's inside the fluid or outside the fluid, but it still get the effect from the gravitational force by that planet, okay. If you live in the deep space, you are not close to any planet, okay, the weight of this object is going to be 0. But when you leave this object close to the on the ground level of the Earth, okay, they would get the effect from the attractive force caused by the Earth, right? And that's how is the weight of the crown. Okay, and there will be another force too, right? Because once you know, you have just learned that there will be buoyant force, the force that try to lift this one up, right? Okay, let's draw this force with this different color. Okay, there will be a force here which is denoted by B, right? Let's summarize this. This is in equilibrium state, okay. The crowd just stay like this, okay, it doesn't move at all. It's in the static condition. We would apply the first law of the first Newton's law again, C by F remains 0, right? And let's say pointing up is positive, okay, it's positive. If pointing up is positive, we're going to have T2 as plus, okay, and B2, B would be also plus, right? And W crown pointing down is going to have the coefficient as -1. W crown remains 0, right? And yeah, what we don't want to know, we didn't know yet, is this one, right? Our destination is V crown, which is this one, right? V crown is the most important thing. V crown should stay inside this, right? Should be here, okay? And yeah, you know that T2 is this number is only T2 is only this number, okay? And B is right here. We move this one to the right hand side, you would get B, okay. Yeah, from what we have seen before, right? The expression of the B is going to be rho F, right? Rho of the fluid times the volume of the object, right? And times G, right? And on the right hand side, you would have W crown minus T2, right? And you have your own target, right? V crown, which is the volume of the object too, right? So V crown is going to be the difference here, this term, right? Divided by rho F and G, right? So we are going to have W crown minus T2 divided by what is that? It's rho F, the density of the fluid, times the gravitational acceleration on Earth, right? So let's get into the detail of this calculation. You would know V crown. The volume of this crown is W crown is what you have seen here, which is the same value as the tension in the first situation, right? First experiment. 784 minus T2. T2 is the value you could observe from the spring, from the weight measurement device, 686, right? 686 divided by the density of this fluid. There she throw the crown into the water, right? This is the keyword here, in water, right? So we would have the density of the water, which is 1,000, right? 1,000 kilogram per cubic meter, and the gravitational on Earth is 9.8. Okay, you leave these quantities into the calculator, right? You would get the result. All right. Yeah. You get this value right here. Okay. In the calculator, right? Yes, 784,686. Where is that? The volume of crowd will be 7.84 minus 6.86 divided by, what is that? It's rho, right, which is 1,000 kilogram per cubic meter, and the gravitational on Earth, okay, we have 9.8, and that's the value for the crowd. Okay, it's 10 to the negative 4. Okay, 10 to the negative 4. We have 10 to the negative 4. It's not approximation at all. Okay, it's the exact equality, so it's going to be cubic meter, and our destination is rho. We have got already the volume of the crowd, but what we actually would like to know is the density rho crowd. Okay, the division of two quantities. So therefore, the density of the crowd will be the mass, right, which is what we have prepared for. It's 0.8 kilogram, right? 0.8 divided by the volume of the crowd, which is 1 to the negative 4. So we have finally 8 times 10 is negative 3, right? Kilogram per cubic meter, or simply 8,000, right, kilogram per cubic meter. But this is not the answer. Okay, it's not the answer, because the question is whether this crowd, this object, is the genuine one or not. Is it made of pure gold or not, right? And as we have observed before from the table, the density of the pure gold is 19.3, okay, which is quite heavier, more dense than what we have got here, which is only 8,000. There you have rho crowd less than the density, right? Density of the pure gold. Pure gold is 19.3, okay, 19.3 kilogram per cubic meter. All right, so it's not the case, right? Because what you could get here, okay, it's fraud, okay. It's fraud. This purchase is not good at all, because what you get is not what you expect, because the density crowd density is not exactly the pure gold density, right? Pure gold density. So we end up, or we get a conclusion like this: the crowd density here, the density of this object, is not exactly the same value of the pure gold density, okay, in the experimental room by the physicists. Okay, so what should we do then? Because we could not get the true value of the pure gold density from our object. Yeah. So let's analyze what could happen. Okay. Of course, it's lighter. You could see the density of the cloud, which is only 8,000, less than 19, right? The value of the density of gold density is 19.3 times 10 less 10 to the 3, right? But oh my god, okay. But this one is only number 8, right? Number 8 is less than number 19 for sure, right? So this one is lighter, a little bit lighter. So what is the reason behind that? Yeah, the seller may have made the I don't know, the not genius one, the pseudo one, right? The not the pure gold, right? The seller may mix the gold with any other material substance like silver or lead. They may just pour the lead, okay, during the hot process, and they just pour other stuff inside the gold, and it still looks like gold, right? But with the same color as the gold, but inside this material, once they get cold, right? Once it gets cold, it's not 100% made of gold. Okay, it may contain other stuff, or in another case, the seller didn't mix any material also, right? They didn't mix the other substance also into this crown. Okay, the color of this crown looks exactly the same as the color of the pure gold, but in other sense. อันนี้ไม่ได้บอกชี้โพงให้ก็ลองให้คุณไปหาหลอกคนอื่นครับโอเคไหม but what is going on in the real society is that it can happen that they just make a hollow inside the piece of the gold. Okay, for example, this piece, okay, you just let the air get into the empty space, get into this piece of the cloud, okay, or you have the area of the air, okay, staying inside this component of the cloud. It could also increase the volume, but the weight is less than that. For that reason, that's you get the lower density of the cloud. Okay, it's also possible in that sense. Okay, they just make the hollow inside this piece. Okay, the big part of the cloud. Okay, it may contain some hollow, some air bubble inside. So yeah, that's why you can save the amount of gold. Okay, and someone could not be observed by eyes. Okay, except that you have a special microscopic camera or something like that. Okay, you will be able to see through the material inside, right? So yeah, so we end up with the condition that this cloud is not made of pure gold. Okay, it may contain contamination, other material, other substance. Read, they may also pour some iron, okay, into this and other kind of metal, okay, aluminum or silver, okay, which is cheaper than the gold, okay, for incorrect reason. Okay, we have finished it or completed this question, right? Let's go. I'm not sure whether, let's check the reason. We get 8,000, right? Yeah, we get 8,000. Okay, and the reason is the gold the crown may contain hollow, or it's not made of pure gold, or both. Okay, also the seller just also include the hollow and mix some other material into the crown production process. Okay, they just mix other material too. Okay? It's also possible. All right, now we we finish this example. Let's move to another one มีหลายตัวอย่างนะครับเรื่องนี้นะครับฝึกซ้อมให้คุณจะได้เก่งครับ okay solid gold statue, right? Solid gold statue, it's taken from the book number 2. From in this one is taken from the book number 1. This one is taken from the book number 2. Okay, 15 kilogram. Okay, you know this is the amount of mass, right? The mass of solid gold. Again, okay, we are talking about gold. I don't know why people are interested in gold. Okay, you know that before our generation, the chemist, okay, the people working about chemistry are trying to convert any material into a precious object, right? Because everyone would like to have money. Everyone would like to be wealthy, right? You also want to have more money when you are grown up, you have family, you want more money. And one way is that you try to have something precious, for example, property, the land, the car, and whatever, right? But gold is a precious stuff. And in the ancient generation, in the former generation before us, the chemist, the people working about chemistry, were trying to convert any material, okay, any element, any substance to be gold, because the gold is very, very expensive. It's extremely expensive, right? When you have more gold, you are more wealthy, right? Wealthier than other people. Yeah. And one of the objects in chemistry is that they try to study the property of elements, and they try to convert any elements into the gold, right? Because they want to have more money, more to keep some precious stuff, right, with them. Yeah, that's why they are interested in gold. Okay, as 15 solid gold statue is being raised from a sunken treasure ship. Okay, you know, you have ever watched the movie, right? And the movie was about the thief and so on, who just rob and steal some precious thing from the king's palace and so on. And of course, in the king's palace, there will be some decoration components, for example, the crown and so on, which are made of gold, right? And yeah, once the authority of the palace try to catch the thief on the ship and so on, and they want to escape from this punishment, right? They just throw away, okay, what they have stolen into the seawater, okay? And you know that gold is a very, very good material. They can sustain any kind of oxide, right? When they live into, when they stay inside the seawater, which is very, very sensitive to destroy any object, right? Yeah, but the gold can stay inside the seawater without any problem, because they have a very strong bonding force inside the material, inside the molecules, right? Yeah, someday the authority of the palace has discovered this statue, which is very precious, very very worth, right? Very, very expensive, and they have tried to bring this one up, okay, from the bottom of the sea, of the ocean. And yeah, they just let someone to go with screwdriver and lay down the net, okay, the net so that they want to carry this one up, okay. And yeah, during the carrying process by the palace authority, they have the rope here, okay, which is quite similar to the former example, but the liquid which is written, which is shown here in the blue, is still the sea water, right? The ocean water. So yeah, this is not the pure water. And yeah, of course, during this bringing up process, lifting process. We have, of course, if you look it by eye, you will not see anything. But if you look it by physical sense, there will be the weight of this object, right? Let's neglect the weight of the net to carry the statue. Let's say that the weight or the mass of the statue is very, very large compared to the mass of the net or the rope or the string here too, right? Yeah, there will be, of course, the weight of this statue, and there will be the tension force caused by the rope pointing upward. And of course, because these statues staying inside the water, right? There will be also the buoyant force. Okay, buoyant force in the book number 2 is denoted by the F with subscript B. Okay, it depends on you. Okay, whether you prefer simply letter B, like in this expression. Yeah, with the B, right? Here B, or you prefer F with subscript B. Okay, that's a matter for me. When you are doing the homework, you can use either the FB or B. Okay, but don't use those two variables simultaneously. Otherwise, I'm gonna get confused. Okay, use only single form of that, whether it's FB or simply B. Okay, it's fine to me. Okay, I can understand both. Okay, if you do the homework. The solid gold statue is being lasered from a sunken treasure ship as shown in figure 5, and find the tension in the hoisting cable. This is the cable from the hoist. Okay, they have the hydraulic lifting arm, and it's the hoist. There is the hoisting cable, and when the statue is completely immersed, okay, and okay. In the first situation, you are lifting this. You are lifting this statue up by using the hoisting cable. Okay, and that's the first situation. And in the second situation, what is the tension of the rope once the T2? Okay, this is the second situation. This is T1. What is the tension on this hoisting cable or the rope when the statue is out of the sea water completely? Okay, is out of the sea. Okay, they ask us 2 questions, 2 quantities when the tension when the statue is completely out of the water. Okay, let's oh no, my God, no. เมื่อวานนี้ผมเพิ่งไปเช็คนะครับผมส่งไลน์อะไรให้คุณผิดด้วยไหมครับมันเป็นชื่อเปเปอร์ครับไม่รู้ห้อง604หรือ605นะผมเบลอนะครับโอเคไหมทำงานวิจัยเมื่อวานนี้โอเคเดี๋ยวลบให้นะครับลืมนะครับวันนี้ก็เปิดมาก็เตรียมเซตอัพให้คุณนะครับเพื่อสตรีมนะครับ Okay, let's consider the first situation. What is the tension of the rope? Okay, when the object, the statue, is still inside water, right? Of course, in this situation, if we draw the free body diagram of this statue, let's say this is the mass, right? Let's say this is the mass, and we have W, which is mg, right here, and of course we would have the lifting force caused by the hoisting cable. That's the T1, right? And yeah, because this statue is still inside the liquid, right, which is seawater. I don't know. They want to use, okay, actually it's seawater, but from what we can see here, they use simply the value of the pure water density. Okay, I'm not sure whether we have also the value of the seawater density. It depends on different location. Okay, we cannot simply. I'm not sure whether they have also provided the seawater. Okay, of course we have here. Here seawater is 1.03. Okay, 1.03 times 10⁻³ right? Kilogram per cubic meter, and that's the role of seawater like this. Okay, I will change it later. Okay, because in the book they use the density of the pure water. I think it's not correct, right? Because the statue would not be thrown away inside the true water. It should be in the ocean or in the sea and so on, right? So we have to deal with we have to use the seawater density, which is right here. I'm not sure whether they have also no, the pure water is like this. They don't have seawater in the first table, but in the second table we can see the seawater density. So it's 1.03. We're gonna use this one, okay, instead of the ideal case. Okay, the density of the seawater would not be exactly the same as the pure water. Okay, the statue problem, right? This one. Okay, right now we want to find T1, but we would have also the buoyant force, right? Lifting force here, which is B, okay, or FB, up to you. Yep, B here. And according to the first Newton's law, when the object stay like this, right? Let's say it's in equilibrium state. So this is the positive. Oh, sorry, my God. Okay, let's say this is the positive. This one is positive. Okay, it's positive. And then T1 is going to be plus, right? T1 is going to be positive plus T. Oh, I should not say plus, it's not correct. It should be positive. T1 is positive and B2, right? B should be positive. And W is going to be negative, pointing in the opposite direction, negative, right? So from the first Newton's law, we have sigma F equal to 0, right? So yeah, T1 up, T1 up plus B and minus W, right, equal 0, right? And but what we want to find is T1, right? We need to move every term to the right hand side, all two terms. So T1 will be W minus B. W is the weight of this object, right? And they say the mass of this solid statue. I don't know how they could know the mass of this object before. Okay, maybe this is the specification of the detail that is written in the palace before, right? It could happen in that sense. Of course, it's mass of the statue times the G, right? And minus B is the buoyant force, right? The rho FVO, right? Rho FVO times G, right? Let's open another page, right? It's mg, right? T1, right? And m open parenthesis m minus rho of seawater times the volume of statue, right, times the gravitational acceleration on Earth, right? And as you know, the mass of this statue is 15. That's the detail written in the data sheet in the palace is 15 kilogram minus, we are going to use the seawater density right here, okay? It's 1.03 เราจะไม่ใช้ค่าเดียวกับในที่เฉลยนะครับดังนั้นคำตอบจะไม่เท่ากันนะคุณอย่าตกใจนะครับผมจะใช้ค่าจริงดีกว่า1.03 times 10 to 3 and the volume of this gravitational of this statue, my god, what is that? We don't know the we don't know the volume of the statue. How could we find it? Because times what? And here times t, right? We don't know the volume of statue. The volume of statue is unknown. We don't know. Do you know any of you? Is there any of you who know this? มีใครทราบไหม Who knows this? มีใครทราบไหมครับว่ามันกี่อะไรยังไงครับมันกี่ลูกบาศก์เมตรอะทองอันนี้นะครับพอทราบไหม Any idea about it? Who could find the volume of this statue? Any of you who could find this? จะมีคนไหนพอทราบไหมครับว่า มันสรุปแล้วเขียนผิดเขียนผิดกรณีของเขาเลยห้อง5เขาทำกันบ้านมาไม่รู้เขียน100 นิวตันหรือกิตภพนะครับเข้าไหมกิตภพไม่เกี่ยวกับคุณเดี๋ยวผมถามเขาเรื่องกันบ้านสรุปเขาจะเอาyeah it's อัครวัตนะครับอัครวัตส่งมาคือเช็คชื่อใช่ไหมอัครวัตผมไม่ได้ผิดอะไรใช่ไหมครับอัครวัตส่งมาอัครวัตส่งรูปอัครวัตเช็คชื่อแล้วก็ส่งแคปเจอร์หน้าจอมา Okay, all right, I understand that, but we are right now at a problem. We don't know the volume of this object of the statue. So any of you who could help me to this? มีใครพอจะช่วยผมได้ไหมว่ามันต้องเท่าไหร่ครับนี่ All right, what is that? Any of you who could help me? We don't know V statue. If we know V statue, we're gonna have T1 easily, right? So what should we do then? ทำไงได้ครับ มันไม่ทราบครับเลิกทำนะทำไม่ได้แล้วอะไรอย่างนี้we don't know the value of the density, right? I'm gonna try to capture the screen picture to you, right? This one and the line shot. The line shot. Where is that? This one or the first one, I'm not sure. (604). Yes. 604. Okay. Yep. No one could tell me right ไม่มีใครตอบได้เลยว่าหา V state 2ได้ไงพิมพ์ได้ไหมมีคนไหนพิมพ์ได้ไหมครับขี้เกียจตอบอาจารย์แล้วครับเงียบไว้ดีกว่า all right yes I think this is the case I don't know which one is yesมาแล้วครับอันนี้รูปที่คุณเช็คชื่อนะของที่ซูมนะครับมี2คนนะ but for the other I don't know มันยังไม่ขึ้น CPU ใช้เต็มสปีดอยู่ครับตอนนี้ alright yes the V state right so let's get back to the definition of the density is rho right rho state and what type of material does is this state made of is made of again the pure gold right so let's get back to the previous problem we know that we have just checked whether the crown is made of pure gold or not we found that the theoretical value of the gold density is 19.3 oh sorry for that we have misses 10 this is 2 3 right it's not 103 10 to the 3 okay yes we have to use that value and yeah rho statue is actually raw gold right it's made of pure gold the palace is full of money they can build up anything because they have a lot of money okay and yes the yeah they have a lot of money and they can build up anything as they want okay the king has a lot of money เดี๋ยวครับผมแคปเจอร์นิดนึงนะเดี๋ยวอยู่ดีไฟดับขึ้นมานี่ผมสวยนะครับทำอะไรไม่ได้ครับ CPU เต็มครับกำลังสั่งคอมใหม่ครับ Mac mini มาเพื่อไม่ให้มันตีกับงานวิจัยที่ผมกำลังรันอยู่นะครับแล้วผมใช้ไลฟ์สอนคุณด้วยนะครับจะใช้อีกเครื่องหนึ่งนะครับโอเคthe yeah low goal is 19.3 right times 10 to 3 yeah which is 19.3 times the density of the water and raw gold is the volume of the statue divided by the I'm stupid is the mass not well one volume stay at the denominator right this is the m the mass of the statue divided by the volume of the statue right and what we want to know is the volume of the statue right? Which is this one right this one is unknown we would like to know and we move this one to the left hand side of the equality and we move the density to the right hand side staying at the denominator position the lower position we would get a V statue V statue equals the mass of statue divided by the density of the gold right now we are using the condition of pure gold to the statue because the statue is made of gold the gold doesn't change with any collision by the seawater okay it stay in the same condition okay let's say something like that and yeah let's go ahead with that you know that the V statue is it is value right we're gonna substitute this one okay this ratio into this expression we're gonna get T1 right now okay let's go ahead with that T1 now would be able to be found by our density of the statue okay the correlation yes it's m right m minus rho of the seawater, let's say SW for abbreviation. Seawater is SW. And the volume of the stator is going to be M stator, and we'll go, right? It's M stator divided by the density of the goal. And we have also the gravitational acceleration on Earth here. Okay, the mass is, of course, 15. And the density of the seawater 1.03 times 10⁻�3. Okay, and the ratio here is the mass of the stator, which is okay. It's I'm stupid. This is the same thing, right? So I'm sorry for that. M here and M here is the same, right? M here and M here is the same. So we move M to the front. We're going to have mass of stator times G, right? Times G, and 1 minus rho of seawater divided by rho of the goal, right? The goal. We get that, right? Now let's substitute the numerical expression. Mass of the stator is 15 kilogram, and the gravitational acceleration on Earth is 9.8, and 1 minus density of the seawater is 1.03 times 10⁻�3, and density of the gold is, as we have seen before in the previous problem, 19.3 times 10⁻�3, right? And you could see that this is the cancellation, right? It's somehow like that. And if you go to the numeric by hand, okay, without any calculator, yeah, there you have 15, still have 15 and 9.8, and here you have 193 minus 1930 minus 103, right? Divided by 103, right? And you're gonna get the result, right? Which is เดี๋ยวคุณเลิกเท่าไหร่นะ 12:40 what time 14:20, right? So it's time, it's over now, right? I'm sorry for that, but let's complete this one first, okay? Let's go to the calculator, right? It's T1, right? We're gonna finish soon. It's 15 times 9.8 and times 1930 minus density of the seawater 103 divided by the 103, right? And that's the first string tension, 2607.5. It's approximately 2607.5 Newton. And let's check whether it's correct or not. ผมก็ลืมดูเวลานะครับทำมาจนเกินไปเลยนะครับเกินเวลาคุณโอมT1 oh I'm stupid, it's incorrect. It's row water by 19, right? Sorry, this one is incorrect. It's 1930. I'm sorry for that. This is incorrect. Where is that? 13. No, it's 1930 นะ604ขอเลิกใช้นิดนึงเพราะว่าเสียเวลาเซตเครื่องโอ้ sorry เสียเวลาเซตเครื่องตอนต้นนะครับ139.15 it's 139.15 Newton. Okay, that's the string in the first situation, right? The one it's still in the water, right? Okay, sorry for that. We have to quit the lecture right now because it's time for M605. For M604, I'm sorry for that. We're gonna see it later. Okay, next on the upcoming Friday morning. Okay, 604นะครับสวัสดีครับบ๊ายบายครับเดี๋ยวส่งรูปจากการแคปเจอร์ให้นะครับสวัสดีครับการบ้านไม่มีนะครับ604ถ้าใครไม่มีรูปก็604ถ้าใครไม่มีรูปก็แจ้งมาส่วนตัวนะบางคนแจ้งมานะครับพวกกสิดิตพวกใครนะอีกคนอัครวัฒน์นะครับโอเคไหมก็คุณก็นะครับก็ปอชื่อจริงเลยนะผมจำไม่ได้แล้วนั่นแหละส่งมาแล้วปประภาวิทย์ใช่แล้วประภาวิทย์ก็ส่งรูปมาครับเพื่อชัวร์ความชัวร์นะครับโอเคไหมก็โอเคyes two people and some ธนกรปนทัพ Okay, now it's time for M605, right? Let's check whether the M605 just live right now, and some of you have written สุรปวีณนี่ห้องอะไรห้อง4ครับสุรวีณนะเขา605คนแรกที่พิมพ์ก็คือสุภวิทย์นะครับใช่ไหมสุภวิทย์สันติสุภวิทย์นี่เป็นผมจำได้เขาจะเป็นคนแรกๆที่ส่งกันบ้านนะจำได้ครับโอเคก็นับถือนะครับขยันกว่าผมด้วยนะเคยไหมokay yes we are 3 people right now and just let's go ahead with that. All right, let's go ahead with this. So it's a pattern, right? Okay. Anybody is right there, right? ถ้าเข้าช้าเนื่องจากติดวิชาอื่นหรือคุณทานของว่างนะครับหรือทานของว่างเนื่องด้วยเบรกอะไรนะครับเรียนมาทั้งวันนะผมไม่มายเลยนะครับโอเคไหมคุณเข้ามาสาย15 นาที20 นาทีผมไม่ซีเรียสครับโอเคไหม3 people in Zoom and 4 people in the YouTube channel, right? ถ้าใครสนใจดูที่อันนี้นะซึ่งเป็นถ่ายจากหน้าจอนะครับอยากเห็นมือผมเขียนด้วยก็ดูตรงนี้ได้นะครับโอเคไหมถ้าอยากดูนะครับเสียงก็น่าจะดีด้วยมั้งมันใช้กล้องใช้ไมโครโฟนจากมือถือนะครับโอเคไหมก็โอเคgood afternoon everybody. M605 is a great time because we didn't waste our time for preparing the connection or setting up the Zoom and the YouTube channel at all, right? Sometime in M604 section, we have lost some the time for that stuff. Okay, for M605, it's already there, and yeah, we are gonna continue our story, right? You have seen the application of the lifting force. Okay, it's known as Boyong force, right? We arrive at this topic. Welcome all of you to SCI33206, which is physics number 5, right? It's good that none of you is on live whether in M604 or M605, right? Okay. Yes. Here is the class, right? And you have this device, okay, which is called hydrometers. Okay, whether in this form or in this form. Okay, they have several forms for the hydrometer. The functionality or the task of hydrometers is that we use this device to measure the density of any fluid. Okay, we use this device to measure the density of the fluid. For example, you have a glass like this and you have already liquid or water fill it in, just throw it away, leave this one into the liquid, and it's gonna stay upward like this. Okay, stay vertically. Okay, stay vertical like this, and you just read the scale. Okay, the scale what you observe here is the number 3.4 or something like that. Okay, you get that value, and that value is the density of this fluid. Okay, the blue fluid here. Okay, that's the first way. The second way is that you leave this device inside a smaller smaller tube, okay, you would be able also to observe the number here on this scale, okay, and you get the density in this one คราวที่แล้วนะครับมันมีการบ้านนะที่คนทำเรื่องที่คนทำโจทย์อันหนึ่งมานะครับที่พิสูจน์ตามตัวเลขตามตัวหนังสือนะว่าได้ true ไม่ true มันจะมีมาโนมิเตอร์นะครับโอเคไหมมาโนมิเตอร์ก็ทำจากประหลอดนะครับโอเคไหมผมก็ศึกษาเพิ่มเติมแล้วก็ส่งรายละเอียดต่างๆให้คุณไปนะครับไปในทางหลายรับส่งดึกๆอะไรผมขออภัยด้วยนะเพราะว่ากลางวันผมก็จะยุ่งเกี่ยวกับกลางวันก็จะยุ่งเกี่ยวกับงานอื่นจิปาถะนะครับเขียนงานตัวเองงานวิจัยอะไรอย่างเงี้ยนะครับทำให้มันนึกหรือบางทีคุณส่งการบ้านมาตอนกลางคืนเนี่ยผมก็พยายามรีบตรวจให้คุณทันทีโอเคต้องขอประทานอภัยนะเพราะคุณเวลาพักผ่อนคุณนอนหลับอะไรอย่างเงี้ย Hydrometers are devices for measuring the density of a fluid like this in the hydrometer floats higher in a denser liquid than in a less dense liquid. Okay, if you leave this one in water, you get a deep portion right here. But if you leave the hydrometer into the mercury, okay, mercury liquid form, you would get a small distance here, okay, because mercury doesn't allow anything get into their substance so much, okay, because they have a high density, okay. High density means the strong attractive force among several molecules in that material, in that substance. All right, hydrometer flows higher in a denser liquid than in less dense liquid, okay. The fluid that is more dense, okay, it cannot float so high. Okay, yeah, like this, right? Okay, and it is weighted at its bottom end so that the upright position is stable. When this part is quite heavy, okay, so that it can stay vertically, okay, in the equilibrium state. Okay, it doesn't move anymore. And scale in the top stem permits the direct density readings. Okay, there is a scale written on this straight line. Okay, and you could see it quite simply from this bar, from this scale, right? Okay, ขออนุญาต chapter หน้าจอนิดนึงครับแค่มา and this one to write. Yes. Let's move to the next page. We have another application which is in the same kind of hydrometer. We use this principle, the density of any material or any substance, to monitor the condition of that stuff. Okay, and one thing that is already used in the past or even nowadays and in the current situation is the observation of health condition of the battery. Okay, whether we want to see whether our battery is in a good condition or not. Okay, and how is it? Okay, let's say this is the 12-volt battery. You know, the battery inside the hood. Okay, for some cars they have battery at the rear part in the rear trunk. Okay, and for most cars you can see the battery inside the hood, okay, in front of the car. Okay, in whatever position, okay, there is the main or major type of battery that uses the lead acid substance as the chemical agent in order to generate the electric current inside this battery. Okay, and the amount of electric current depends directly on the density, the concentration of the acid in this liquid. Okay, Okay, this liquid is a mixture of pure water. It should be pure, okay, so that there is no internal resistance at all. Okay, if you have no pure water, there is going to be internal resistance, and it will obstruct the current flow, okay, out of the battery, and it's not good, okay, because you have reduced power, you have deteriorating power or ability by the battery. Okay, it's better to use the pure water. Here, this liquid is a mix of pure water and the acid. Okay, and they have the lead here, right, in the cell. Okay, yeah. Because of this special chemical mixture, right? If you put the current into this one, okay, it's going to have ion, okay, ionization. We cast the positive and negative charges into this liquid. And once you don't charge or you don't let the current get into this battery, you want to use the current, okay, out of this. You just connect the copper wire and the current, okay, which is the mix between positive charge and negative charge under the chemical process. Okay, the proton, oh sorry, the electron is going to go out of this battery, and it means you have current flow, right? Okay, for some days, okay, at the beginning stage, okay, you got the new battery, everything works fine. Okay, the condition of this is okay. Okay, it's perfect. It works good. For one or for a few years later, the condition, the concentration of the acid per pure water here is diminished. Okay, the ratio between the acid and the pure water has changed. So now this liquid is not in a good condition to deliver the current to other components at all anymore. Okay, so yeah, the engineer or the person who builds this battery observed that the concentration of the acid depends on the density inside this fluid. So they include a new component, which is made of 3 pipes, okay, these 3 cylinder. The first one is up right here, the second one is right here, and the third one is right here. Okay, if your liquid, which is a mix of acid and pure water, is in a good condition, the density of this mixture would have would be in a high level, and with a high level you would have more force. Okay, this ball is not a solid ball. It's a ball that contains a bubble, the air inside. Okay, when this liquid, the mix of these 2 liquids, is in good condition, you have high density of this mixture. The high density will bring you more lifting force, okay, to this ball, and this ball would stay somewhere here in this portion of the pipe. Okay, and they just drill this hole open, okay, and they leave this part open so that the owner of the car or anybody could look at this hole. When you observe the ball from this hole, and if you could see it, it means that the battery is in a good condition. Okay, for some years later, a few years later, when the concentration of the acid per water here is not good, it's not in a high, it's not in appropriate amount anymore, the density of this mixture decreases or reduces. There will be no lifting force. There will be no strong lifting force anymore. the ball here would stay into this part, right? It would stay in this part. And if you take a look from this hole, you would not be able to see the ball anymore. And we use this principle to observe whether the battery is in a good condition or not. But the idea behind that is what we are going to study here. It is known lifting force or buoyant force, okay? The lifting force is the force that tries to lift this object up, okay? And that's the way we observe the battery condition. Okay, yeah, we often say that an object placed in a fluid is buoyed up by the fluid. So we call this upward force the buoyant force and denoted by the letter B. Okay, in some books, they would also use this notation, this variable F with subscript B. Okay, it's quite straightforward, buoyant force, right? F stands for force. But for simplicity, we use B here in this lecture. But please note that it doesn't mean we have, we are talking about the magnetic flux density as in the former semester, okay? We don't talk about magnetic flux density, which is also denoted by the letter B anymore, okay? Forget about it. B as the magnetic flux, okay? That's what is in the past, okay, in the last previous semester. Okay, the average density of an object is what ultimately determines whether it floats or not. Okay, I don't know whether you have plays with this. For me, I have grown up. I was grown up in the rural area. We played with the crawl, okay, the soil. And a kind of soil in we try to build up an object which has air inside, and the good person is that any person who could make that object to float on the water, okay, and that's actually relies on the idea of density here, okay. Any object will float or sink, okay, on it. It will depend on the density, okay, compared to the density of that fluid. Okay, มีคนพิมพ์เข้ามาเยอะครับจริงๆมันเปิดหลายช่องนะคุณดูที่ไหนก็ได้นะครับโอเคโอเคoh no it's M604&M605 right okay 605 right okay now let's make the judgment okay make the decision whether that object is going to float or sink into the water. Okay, on the left side we have a mass, we have an object, right? It's in the cubic shape like this, width, length and height, right? It's a cubic, and yes, you have also the you have also another object, okay. This seems to be a kind of wood, right? This seems to be a kind of metal, right? It's bronze or it's any kind of metal. Okay, in yes, the first experiment is up right here on the left, up right here on the right as the second experiment. And each substance, whether it's wood or metal, would have its own density, right? We say it's object density rho with subscript obj. And the fluid here is any kind of fluid. It can be either mercury or water. Okay, it's up to you. And yeah, once you let something, stay inside the water like this, and when the density of this piece, this cubic, is less than the density of the fluid, this object is gonna go up, okay, it's called floating acceleration, right? It's gonna stay on top of the water surface here. But for the substance that is heavier than the water, okay, is more dense than the liquid. It has more density than the liquid density. So this object is gonna go down, okay, and stay at the bottom of this container of this glass, okay. And yeah, they say object more dense than the fluid sinks, and object less dense rises, okay. The one here will sink, okay, and this one will rise, okay. And we consider the object that are totally submerged into the fluid. Let's say this one, the second situation. The rho, let rho f be the density of the liquid in both containers, both glasses. Let rho with subscript small o, right? Small o be the density of the object, and we have the last parameter of quantity, which is VO. Okay, VO is the volume of the object, be the VO right here. And the buoyant force can be computed by the displaced fluid weight. Okay, what is that displaced fluid weight? The lifting force or the buoyant force, okay, is simply the weight of the displaced fluid. What is that? So if you let the water stay exactly in the same level of the edge of this container, and if you throw away any object, right, the object would stay inside this liquid. And of course, the increasing volume due to that object will make the water some amount of water to get out of this cup or this container, because the level of the fluid before is exactly at the edge of this container. So yeah, the amount of water that gets out of this glass, okay, will be exactly the same amount of that material that you throw in, okay, especially in terms of volume, okay. Any volume of this object, okay, will try to stay in this glass, and there would be also some water which has the same volume of this material getting out of this container or this glass, right? Okay, and yeah, and if you collect every piece of water from this exceeding process, you would get the weight of that water, okay. The weight of the whole amount of water will be equal to the lifting force here. All right, yeah, and this is the reason why we have the so-called buoyant force, okay. And in qualitative way, buoyant force is equal to the mass of the exceeding liquid, right, which is the density of that fluid times the volume, okay, substituted by the size of this cubic, right, this object, which is VO, V object, that's the mass of the exceeding water, times G. G is the gravitational acceleration on Earth, okay. If you live in any kind of planet, just use the acceleration of that planet. If you live on Mars, just use the gravitational acceleration by Mars. But we are here mainly 100% on Earth, okay. I'm not sure whether one of you may ไม่แน่นะสมัยคุณอาจจะมีโอกาสได้ไปนอกอวกาศก็ได้นะแต่ผมชีวิตผม 100% ผมอยู่บนโลกนะครับผมไม่รู้ว่า G นะครับแรงดึงดูดของดาวดวงอื่นมันหนักมันเบาอะไรกว่ายังไงนะครับโอเคไหมmaybe in the future you may have a tour to travel out of the world, right? Okay, the buoyant force can be computed by the displaced fluid weight, which is this one, right? Mg and low f and v object times c. The weight of the object is calculated from, okay, the weight of this one is, of course, is the product of the mass and the gravitational G, right? But the mass of this object is going to be the product of the density and the volume of that subject, right, which is MO, right? Yeah, it's quite different, right? And if you consider the second law, okay, second law of Newton's, sigma F equal MA, right? Okay, in terms of vector too, right? In this case, there are two forces acting on this object, right? You can see the length of this vector, so it's quite high, right? The lifting force is quite high, and oh, sorry for that. Opening up. Hello, ครับ Hello, ครับ Hello, ครับ ครับกำลังพูดอยู่ครับครับครับมีครับผม3 ชั่วโมงที่แล้วผมไม่ได้ถือมือถือไว้ครับช่วยมาส่งให้หน่อยนะครับเพราะผมรีบใช้จริงๆใช่ครับได้เลยครับเชิญมาส่งเลยครับที่ครับที่เดิมโทรมาก่อนได้ครับผมอยู่กับโทรศัพท์ครับได้ครับด้วยความยินดีครับครับขอบคุณครับครับสวัสดีครับ Oh, I'm sorry for that นะครับก็นะครับผมสั่งคอมพิวเตอร์ไว้นะครับผมสั่งคอมพิวเตอร์ไว้เพราะว่าคอมพิวเตอร์ที่ใช้สตรีมให้คุณเนี่ยครับที่สอนคุณอยู่เนี่ยคือเป็นคอมพิวเตอร์ที่รันงานไปด้วยนะครับแล้วมันจะ CPU มันเกินแล้วนะครับ CPU เต็มประสิทธิภาพทำให้อาจจะมีสะดุดนะครับผมจึงต้องสั่งคอมพิวเตอร์ใหม่เพื่อว่าไม่ให้งานสอนนะครับให้คุณเนี่ยมันสะดุดนะครับดังนั้นโอเคlet's get back to our story yes this is the floating and sinking condition, right? Sigma F equals MA, right? As the second law by Newton, you could see here that the absolute of the magnitude of the Boyon force is greater than the absolute of the weight, right here. And in this case, the absolute of the weight is greater than the absolute value of the Boyon force, the lifting force, right? So you would be able to make a decision. Okay, you would be able to see how the nature make a decision, right? Yes, from the second Newton's law here, let's say everything pointing up like the y-axis, like his y-axis. The quantity here is positive. All right, let's say the thing pointing up is positive, okay? And you will see that B pointing up, right? You have B minus the weight, right? Minus weight, will be MA, right? So A, which is the direction here, is going to be up to, right? Because B is greater than W, okay? The amount which is greater than this thing, okay? This one is greater than this one, you would get positive value of that, right? But for this case, you could see that B, the same thing, okay, B minus W equal MA, okay, because we assume that anything pointing up is positive, and yes, but the B minus W here is going to be negative value, right? So negative value less than 0, right? Because W is greater than, so A would also be negative value. So it means the acceleration of this object is gonna point in the opposite direction to the y-axis. It means this object will go down, okay, because the weight is greater than the lifting force or the buoyant force. Okay, you get that, right? Okay, yes. And if you really want the acceleration, you just move M to the left-hand side, right? So you get the amount of acceleration. That's the result from the second law by Newton. All right, so for us, B minus W is simply the subtraction or the difference between equation 75 and equation 76. Okay, just make the subtraction of these two equations. Okay, B and minus W, right? B minus this term minus this term, right? Which is written here, rho A VO, rho O VO, right? You get this expression, okay? Simply the deduction of these two things, difference of these two things. Well, you could observe that, you could see that there are two factors that are identical to both terms, right? The first one is the gravitational acceleration on Earth, the variable G here. The second one is the variable VO, okay, the volume of that object, okay, is the same. So we move the common variables such as VO and G out of the difference. We get the common term at the end. We have the difference of the density between the fluid and the density of this object, whether it's wood or it's metal, whether wood or metal. Okay, then we get the difference between weight and buoyant force, right? Equation 77 is somehow that, and this is for sorry, B minus W is the relation for finding the acceleration for the floating or upward force of the object. And for the object that is more dense than fluid, we would consider the floating situation, floating acceleration, right? Yeah, in this case, W is greater than B, right? So W stay first and B stay at the second portion later, right? And yeah, the difference is going to be the same, okay, except for rho O, okay, stay in front of the rho F, the density of the fluid, right? Yes. Now we take a look at or consider another realistic situation when the object doesn't have the center of mass at the not at the center of that object. Okay, let's say the center of gravity of this object is a little bit far away from the center of that mass. Okay, we have CG of the object right here. Okay, not at the center. But as you know, we have the buoyant force or lifting force, right? So but the fluid doesn't know the detail of this object at all. They don't know where the center of mass or center of gravitation of this mass is, right? So the buoyant force is going to act at the center of this object. Okay, where you would get something like that. Okay, and yes, once you have these, that's the beginning situation. Okay, and when you let the time goes by, this force tried to bring this one up, and this force tried to bring this location down, right? This object, this object, once it for this object, once it moves downward according to the sinking situation, it has more density than the fluid. Okay, this force will try to move the mass down like this. This one is going to point the mass up, but because of the weight is higher in magnitude than the buoyant force, okay, the object will stay in equilibrium state once the two forces are aligned in the same straight line. Okay, when those two forces are in the same alignment, okay, this object will no longer rotate. Okay, it just rotate a little bit at the beginning, and it's gonna stay like this during their floating route, sinking period, sinking process. All right. Okay, that's all of the theory about buoyant force. Now let's apply this so that you can better understand how to use the buoyant force expression. Now we arrive at the first example, which is taken from the book number 1. A bargain hunter purchases the gold crown, okay, at the flea market, the market which sells anything cheap, right? A cheap object. It might be a second-hand object too, right? And yeah, it's an unofficial, and there is no guarantee at all, right? Something like that. But the good thing is that the price here is quite cheap, right? It's not expensive. You would rather walk on this local street and look for the same product with a cheaper price, right? A cheaper thing, right? It's also good, right? Yeah, but the caution, the dangerous thing from this street is that the flea market is that you might get something, you might not get something genuine. Okay, it's something that is fraud, right? It's fraud. It's not the original one, right? And yeah, this lady just walk onto the street. She went to the flea market, this location, and the street, and yeah, she just walked on to this flea market, this street, and she stopped at a shop, right, at sailing point, and she found a crown. Okay, she found a crown, and yeah, it's a ornament, it's a decoration stuff. Yeah, the lady would prefer that, right? And she took a look at this crown, and it seemed to be gold. Okay, and she made her decision to buy it. Okay, with the hope that this crown should be very precious for her, and she can sell it later, okay, with a higher price, so that she can get interest, okay, or benefit from that, the price difference. Okay, and yeah, she carry the gold with her. Okay, what is the shape of gold? Okay, let's say this is the gold. She carried the gold with her at her home. Okay, this is her home, her house. Okay, and she managed to experiment. Okay, the first experiment is that she just hang it. There's spring inside, right? She hang the crown up like this. Okay, and she observed the value here from her eye like that. Okay, and in the second situation, she hang it again with the same weight measurement device. And yes, but in this situation, she leave the crown into, a liquid. Okay, a liquid, and there is liquid surface level like that. Okay, now we arrive at the question during the second measurement. Assume that she has done it with the complete submerged, the fully submerged condition of the crowd, right? The crowd stay fully inside the water, into the fluid here. And the question from this problem is that, is this crowd made of pure gold? Okay. Is this crowd the one that she bought from the flea market? Is this one made of pure gold or not? Okay, that's the question from this problem. All right. So yes, we arrive at this question, and so how could we say whether it's made of gold or not? So question is crowd equal pure gold? Oh, so pure gold or not? Okay, under question. Okay, you have to deliver this question. Okay, it seems like the non-scientific question, right? It seems to be a non-scientific question, but I'm not sure whether it's really non-scientific stuff, or I don't know. Yeah, you would be the person to tell me whether it's completely non-scientific stuff or not. All right. Okay. But actually, this question is scientific stuff. Okay. It's the question that is related to science. Okay. This is the question actually related to science. But we will see later how it involves with our science, okay, especially involves physics. Okay, yeah, let's get into the detail. In order to check whether the crowd is actually equal to the pure gold or not, so we need to use which quantity? Do you think which quantity we are going to use to make a decision whether this object is made of pure gold or not? Which quantity in physics? Mass, weight, volume, density, pressure, boiling point, melting point. Which one would be the right quantity we're going to use to compare those two materials? Okay. Which one? Yeah, because what we have just passed is only boiling force, density, right? What else? Surface tension. What else? Young modulus, stress strain. Which one is the right quantity we're going to use to compare these two materials? The right quantity is density. Okay, we're going to use density to make a decision whether these two objects are the same or not, right? Identity, density is used as identity to verify that this is correct, right? Well, it's like you are a student at the Suan Kulap Vidyalaya school, right? At the SK. For example, I am an authority of the school, and if I would like to check whether you are really the student of Suan Kulap Vidyalaya school or not, one way in order to check your proof or to check your status is to look at your ID card, right? I need to ask for your ID card, and then I can make a decision to allow you to get into the school or not, right? If I am like the card person in front of the school, right? Yeah. In the same way, if we want to check whether this crowd is made of pure gold or not, we have to look for the the density, which is a kind of identity of that object. Okay, you can also use other properties of that object, okay? Because when you complete everything in physics, there are so many ways, right? For example, you can also look at the melting point of this cloud, right? But if you want to melt the cloud down, it means you just destroy the cloud, right? You destroy the object, okay? Because the cloud is already decorated, is already in a good shape, it's suitable to human head. But if you melt it down, it means you destroy that object, right? It's not good at all to use the melting point. One way, which is also clever, is the use of density, okay, which is the property we just learned here, right? So we need to compare the density, which is denoted by the Greek alphabet rho of the cloud, okay, with the subscript of cloud, and the density of the pure gold. Okay, we have to check whether these two values coincide with each other or not. Okay, whether these two values are the same or not, right? Okay, of course, you don't know the density of the cloud right now, but you just try to make the experiment here. You need to know the value of the density of the cloud, but the density of the gold is what you may have, is what you may look for, right? So for example, from any book, from any table, from any source in internet, you could see the actual value of the density of the pure gold, right? So let's get back to the former part of our lecture here. We have already talked about the density of any substance, right? But this one, yeah, right here, we have talked about the density of several stuff, right? Okay, we start from the solid object, from the ice, aluminum, iron, copper, silver, lead, gold, right? Gold here is written as 19.3. Okay, the density of the pure gold is 19.3 times 10 to 3 kilogram per cubic meter, right? That's taken from the book number 1, right? The gold here 19 times 10 to the 3. And from this one, they have also the same value, right? 19.3 times 10 to 3. Okay, that's the same value from both books, book number 1 and book number 2. Okay, please keep this in mind, and we're going to compare it with the density by crowd, right? Let's get into the detail of the density by crowd. You know that from any object, rho is the ratio between the mass of that object divided by the volume of that object, right? But now we are paying our attention to the crowd, right? We're gonna check whether this crowd is made of pure gold, is the proper crowd or not, right? Okay, this should be the good crown for the king, right? Usually the king should wear only the pure material, right? Not the fake material. So this one is density of crown. And also mass here should be the density. Oh my God. ขออภัยนะครับสงสัยมาส่งของสวัสดีครับสวัสดีครับฮัลโหลสวัสดีครับเชิญครับฮัลโหลฮัลโหลครับฮัลโหล oh I don't know what's going on. Okay, yes, we were talking about the density of the crowd, right? สวัสดีครับฮัลโหลครับครับพี่ส่งของใช่ไหมครับมาที่ตึก G ได้ไหมครับตึกสูงข้างหลังครับเอาทำไมผมติดธุระสอนหนังสืออยู่ครับพี่เป็นคนส่งควรจะมาที่นี่เพราะว่าซื้อ iPhone ซื้อ iPad อะไรเขาก็มาส่งถึงที่ประจำครับ Apple DHL เหมือนกันเนี่ยเอาพวกเอาฝากรปภไว้เลยก็ได้เข้าใจใช่ครับใช่ครับเอาก็เข้ามาแล้วกันครับเพราะผมรอรีบใช้ครับตอนนี้ใช้ในงานเครื่องมันเต็มประสิทธิภาพแล้วได้ครับได้ครับโอเคครับผมรอครับครับตึกที่เหมือนเดิมครับขอบคุณมากครับโอเคsorry for that ขออภัยนะครับคือคอมพิวเตอร์นะครับตอนนี้ผมใช้รันงานเกี่ยวกับงานวิจัยด้วยนะครับแล้วก็สตรีมไลฟ์สดให้คุณนะครับ CPU ใช้เต็มประสิทธิภาพแล้วครับดังนั้นผมมีความจำเป็นต้องซื้อคอมพิวเตอร์ใหม่ครับเพื่อมาแยกงานวิจัยกับงานสอนคุณให้ออกจากกันนะครับไม่งั้นมันตีกันอย่างนี้จะทำให้ภาพที่ไปหาคุณนั้นกระตุกนะครับเห็นไหมผมต้องขอประทานอภัยตรงนี้นะครับจะไม่เกิดขึ้นอีกนะครับก็ทำไงได้ครับทำงานที่มหาวิทยาลัยต้องทำงานวิจัยด้วยก็ต้องขออภัยที่เกิดขึ้นนะครับ Okay, let's get back to our story. We crowd the volume of the crowd right here, and the mass of the crowd is our numerator, right? Of course, we don't know yet right now what is the value of both quantity. If we know both quantities, the mass and the volume, we are gonna end up with the density of the crowd, and now we could make a decision, right? If at the end, we get the density of the crowd as 19.3 times 10 raised to 3, we will conclude that our crowd is fortunately made of gold, okay? And this lady is gonna be happy because she bought something cheap and she could sell it later with a higher price and she could get benefit, right? This is the way for so many people doing business, right? Yes, now let's check whether what she bought is a good saying or not, okay? Is worth it or not, okay? So let's, sorry, I don't, sorry, just let's find first, the first thing, we are gonna find the mass of the crowd, okay? And the second step is that we are gonna find the V of the crowd, O2, right? R2, mass of the volume of the crowd, right? Mass, volume, and later the ratio of these one, right? The third thing is find the density, right? Which is rho crowd, right? Just make the division, right? Division, and the fourth step is you have to compare the result to the to the pure goal density. Okay, compare it. Now you end up with the answer whether the crowd is made of pure gold here or not, right? So let's take the first step. Let's get into the detail of the first step. They have measured this device twice, right? The first time she measured, she hang it, where is that? Figure 54. Right? In figure 54, you have, you hang it like this, right? You hang it, this is the result from M604. You hang it like this, and it found that the tension of the string here, of the rope or the hoisting cable here is 7.84. Okay, let's draw the free body diagram of the crown. Let's say it's mass M. It has the weight W, right, which is equal mg, right? And you have the rope which try to pull this one up, all right? This is the tension force at the first stage, okay? We would say it's T with subscript 1. The tension force, okay, caused by this rope or this string pointing upward, okay? And this is in equilibrium state, right? It's in equilibrium state. Yeah. Now we are gonna use the first Newton's law, right? Let's say this is the positive direction, the positive y, positive y. It's the plus y direction, right? We call it positive. So from sigma f equals 0 from the first law by Newton, you get two forces, right? You can see two forces acting on this mass in the vertical way like this, okay? Pointing up means positive. So T1 is going to be positive. T1 is positive. W pointing down is going to be negative, right? It's negative, and you substitute these two values into the first Newton's law equation. So you have T1 as the positive quantity. You have W, the weight of this crown, as the negative quantity. And on the right side, you have 0 because it's in equilibrium state, right? There is no movement. It's everything stay idle. Everything is in static condition. So yeah, you would have W equal T1, okay? And from what she observed here, she made the experiment, okay? She hang it, and she could get the value from the first experiment as the tension string, okay? The string tension here at the first experiment only in the air 7.84. So you get 7.84 Newton for W. Okay, because T1 is 7.84 Newton, W is also 7.84 Newton. Okay, W is 7.84. But you know that in any case, W could be decomposed into the product of M and G, right? So you would be able to find the mass, okay, which is the first step here. We want to find the mass of the crown, right? You would be able to find the mass of the crown from this expression. It is mass of the crown, right, times the acceleration on Earth, right? Acceleration on Earth equals 7.84, right? On the left-hand side, the weight here. And now it's possible for you right now to determine the mass of the crown, which is 7.84 divided by 9.8, okay? And it ends up with 0.8 kilogram, okay? But that's not the answer, okay? We just keep this first, okay? because our destination is to find the density of the crowd, right? The next step is the second one here, find the volume of the crowd. What could we do then? You have to go to the story of this example. It says that she now make a new experiment. She hang the crowd by using the rope here or the string here to the weight measurement device, the spring again. But now she leaves the crowd inside the water, which is surrounded by the container. Okay, here, and now she looks at the number on the scale here, and what she gets by eye is 6.86 Newton. Okay, so in the second experiment, you have this thing, right? So let's draw the free body diagram, the mass of the crowd. You have the tension by the rope or the string here, T2, right, in the second term. And of course, there would be the same thing, which is the weight of this crowd, of this object. But in the second situation, the additional force is going to happen right here, is the Bouillon force, right? Because that's what we have just learned before, right? The Bouillon force or the lifting force here, right? It's the third force is denoted by B. And again, we would say it's positive upward right here, positive, right? There are three forces. CES, right? The first one, T2 pointing up now, it's become positive. The second one, the weight pointing down is negative. The third one, the Bouillon force pointing up is positive, right? Note that we have two forces as same as before, right? But the additional force is right here. The Bouillon force is pointing upward. It's also positive, right? So three forces happens like that. We put it into the first, again, the first Newton law, right? Which is sigma F equals 0 because everything is in equilibrium state. Okay, equilibrium state, right? Everything stay constantly. So we have T2 positive, W negative, B positive. We have on the left hand side T2 plus, right? Negative W and plus B equals 0, right? So เราเลิกเราเลยประมาณ12 นาทีนะครับ something like that. And yes, you're gonna have the left hand side like that. And our purpose is to find the volume of the crowd, right? We have already got the mass of the crowd, which is 0.8 kilogram. We're gonna find V crowd, and later on we're gonna compute the ratio or the division of those two things, right? So let's find V crowd from this expression. And of course, we know that W is from the previous result, right? Which is the same thing here. W is 7.84 Newton, right? And T2 is the observable quantity by eyes, okay, by this this lady's eye, right, which is 6.86 Newton, and the Bouillon force from these experiments. Okay, let's get into the Bouillon force from the theory here. Bouillon force is rho FVOG, right? B is rho F, the density of the fluid, times the volume of that object, and times g, the gravitational acceleration on that planet. Okay, what is rho f? Rho f is rho of water, right? Rho of water, because we are dealing with the water in this glass, right? Let's say she she just leave the crowd into the water in this container. So rho water is going to be 10 raised to 3 kilogram per cubic meter, right? 10 to 3. And the next one is the gravitational V object, right? V of what? V of this one, right? The crowd. VO is V crowd. This is what we are gonna find. We want to determine V crowd. Leave it. Okay, we don't know. And G is the gravitational acceleration on Earth, 9.8 kilo. Meter per second square, right? Meter per second square. Meter per second square, right? You get everything to that, right? Now substitute every term into that expression, right? Yes. T2, yeah, okay, from this term, T2 minus W plus B. B is rho water times V crowd and G acceleration on the right hand side, it's equal to 0, right here. Yes, now we solve this question to the unknown variable, which is our target, our destination, V crowd, right? So we move T2 to the right hand side, we move W to the right hand side, we move rho water to the right hand side, we move G to the right hand side too. So finally, you end up with rho water as the ratio and the denominator, right? The denominator is, oh, I'm sorry for that. It's not rho water. We're gonna find volume of the crowd. Volume of the crowd. And yes, it's rho water. The gravitational acceleration on Earth, and here is W first as positive, right? Sorry for that. W minus T2, right? So you have at the end W as 7, right? 784. 784 minus 686 divided by rho water. Rho water is density of the water. As you know, it's 1 ton per cubic meter, right? It's 1,000 kilogram. 1,000 kilogram per cubic meter, and the gravitational on our planet 9.8, right? You leave it into the calculator and you're gonna get the result right here, which is 10 raised to negative 4. Okay, we put it into the calculator, we get 10 raised to negative 4 square cubic meter. Okay, you could see that the volume of the crowd is not so high. Okay, it's not a big object. Okay, it just takes only, I don't know, 0.1 cc. Yeah, 0.1 cc. Okay, cubic centimeter. Oh, all right. No. It's 100, right? 100 cc, right? If you compare, it's 100 cc, right? Cubic centimeter cc. But it doesn't matter. Our result should be in the SI system. Okay, this SI scale is 10 raised to negative 4, right? Okay, the third step is that we want to find the density of this crowd. Okay, let's go to the density of this crowd. Rho crowd will be mass of the crowd divided by volume of the cloud, right? So mass of the cloud is 0.8 kilogram by 10⁻⁴ cubic meter, and it's actually, what is that? It's 8,000, right? 8 times 10⁻³ kilogram per cubic meter, right? Yeah, that's it. And now we're going to compare it to the density of the pure gold, right? Here we arrived at the last step, compare the result to the pure gold density. Pure gold density is 19.3 times 10⁻⁵, right? So yes, you could see that raw crowd, which is only 8 times 10⁻⁵, but it's not equal to 19.3, right? So low crowd is not equal to rho of pure gold. We end up with this conclusion, right? With this condition. What does it mean? It means that this crowd is not made of pure gold at all, because we compare its density to this gold already, right? So it's not the pure gold, because the density is not the same, are not the same, right? The density of both objects are not the same. We would conclude that the crowd is not made of pure gold. And what is the reason behind that? What do you think? You can see that what happened? I don't understand. Yes, I don't understand. You could see that rho crowd is less than rho gold, right? 8 is less than number 19.3, right? Right, 8 is less than 13.3. So 19.3. So what is the reason? It means that during the building process of this gold, okay, they may have mold and so on, the block that try to build this one up. They may pour other metal, okay, during the melting process into this one and into the gold mixture, right? So they may put something cheap, okay, so that they can get benefit from that, right? Yes, they may put the other stuff into this one too, right? So that they can reduce the amount they have to pay, right? When you don't pour the gold, okay, in the melting process into this component, you can save some money, right? And they may pour something else like lead, silver, or even steel or iron into the mix of these one, right? And they can use other stuff too, right? Copper, right? It's a possible metal. You pour melting metal into this mixture, you can save some amount of gold, okay, because the gold is expensive, and you make the crown and deliver it to the king, right? So that's why we could not get the same value of the density as the gold, right? Another possible way is that you fill some part of this gold by the air, the bubble, okay? You let some part of this crown be fulfilled with the air, okay? If there is a bubble inside this gold, they would have less mass, right? But with the same volume and less mass, you would have less density, okay? Or another way is that you use these two techniques, okay? You mix it with other metal, which is not, which are not gold, or you let the bubble stay inside this gold, okay, so that you could save some amount of gold, okay. It's gonna be cheaper in order to build the gold, okay. And that's the conclusion from this example, okay. The gold is the crown is fake, okay. We didn't get the genuine crown gold, okay, the gold crown, okay. And now we look at the มันหมดเวลาแล้วแต่ว่าผมขอเริ่มโจทย์นี้แล้วกันนะเพราะว่าให้เท่ากับหรือว่าจะเลิกเลยหรือว่ายังไงครับห้อง5ครับ605เอาไงดีต่อแล้วกันนะปานธรนี่เพิ่มพิมพ์มานะครับปานธรมาพิมพ์ตรงนี้นะโอเควรันทรก็พิมพ์ตรงนี้ด้วยนะครับโอเคนะวรินทรนะพิมพ์2ช่องเลยนะครับโอเคเพื่อความปลอดภัยของคุณเนาะก็โอเคต่อแล้วกันนะเพื่อให้มันเท่ากับห้อง604นะครับ KV have a solid gold statue is being raised from a sunken treasure ship as shown in figure 55. Okay, in the ancient generation the people are interested in something that is precious, right? ถ้าเป็นยุคสมัยนี้ก็สนใจของแพงๆกันนะครับคุณต่อไปคุณอาจจะชอบรถอะไรนะรถเฟอร์รารี่รถลัมโบกินีรถอะไรรถอเวนทาดอร์อะไรพวกนั้นที่มัน15 ล้าน20 ล้าน30 ล้านคุณอาจจะชอบสะสมของแพงๆพวกนั้นครับหรือคุณอาจจะชอบนาฬิกาปาเต้นาฬิกาโรเล็กซ์ที่มันราคาเป็นแสนเป็นล้านอะไรอย่างเงี้ยโอเคไหมโอเค gold is one thing, okay, for the people in the former generation or even in this generation, okay, you want to correct something precious, right? Something worth, right? Yeah, gold is one of that thing, and the people in the ancient generation they try to study chemistry. They want to know the purpose of those people is that they want to transform any elements into gold. Okay, when you have more gold, you are wealthy. You can buy many things. You can live well, and that's the purpose. Okay. And also this example, the king in the former has solid gold statue. So what are solid? It means it's not fluid, right? It's not gas form. There is no the meaning of solid here means there is no air bubble inside this object at all. Okay, this is the statue of anything. Okay, but is the good thing is made of gold. Okay. That's the main idea. Okay, there is no air bubble inside. Okay, the density is completely the mass divided by volume of that object. Okay, yeah, the story happens like that. The thief, okay, try to steal this one from the palace of the king, and they carry it onto the ship, and they carry it onto the ship, but the soldier or the authority from the palace has seen this, and they follow the ship of this thief. Then they try to catch this thief on the sea, and the thief just throw this one into the sea, right, into the sea water, so that there is no proof they didn't steal anything, right? They can get out of the punishment, but this statue stay on the floor of the sea, right, or the ocean. So many years later, someone has found this, and they are trying to bring it up. Okay, and some school diver has carried the net, okay, around this statue, around this object, and they connect it to the hoisting cable. They try to lift it up by using the hydraulic arm and so on. Okay. On the ship, they try to move this one out of the water level. Okay, what they have found in the following is that there is a sheet specification, the detail of this statue in the palace, and it's known that this object has the mass of statue as 15 kilogram, right? 15 kilogram อยค่าทีครับแล้วก็จะเลิกกันนะครับโอเคand then yeah they want to know the tension of the hoisting cable ผมก็ไม่รู้แรงตึงเชือกแล้วมันจะได้ประโยชน์อะไรในชีวิตนะทำไมเป็นไรมันเป็นปัญหาทางฟิสิกส์นะโอเคไหมโอเคin the first situation they are trying to lift the statue of this mass. Okay, we draw the free body diagram. This is the tension force. Okay, tension force at the first situation when this is the weight, right? And here is the sea water level, right? You are trying to lift the statue up, right? But unfortunately, when this object staying inside the liquid, there would be also the buoyant force, right? And during this moment, assume that it's in equilibrium situation, right? We have the first Newton law, right? T1 sigma F, right? Sigma F equal to 0. And anything pointing up is again positive. You can also use the direction pointing downward as the positive. It's up to you, okay? Doesn't matter. The answer is going to be the same, right? Positive as pointing upward. And you have T1 positive, right? T1 plus, okay? And negative W, right? And plus B buoyant force equals 0, right? And we want to know T1, right? So we move T1. Okay, we leave T1 on the left hand side because this is what we want to know. We move W to the right hand. We move B to the right hand side. T1 is going to be W minus B, right? And you know that W is the product of the mass of this object, which is known 15 kilogram, right? Equals mg. And B buoyant force is low F VO times G, right? VF times VO and G. What is rho F? Rho F is the rho of sea water, right? Which is 1.03 times 10. This is 3 kilogram per cubic meter, right? And G is the acceleration on Earth, right? VO, what is VO? VO is the volume of this object, of this statue, right? VO is the volume of the statue, right? And we don't know that, right? But from what you have seen earlier, the density is the mass divided by volume, right? So you have rho is m by v, so v is going to be m by rho, right? We use this relation for the statue because volume of the statue is going to be mass of statue divided by the rho, the density of the statue. But what is the density of the statue? Assume that the palace is rich, okay, it's wealthy. They made the statue of pure gold. So we're gonna end up with we statue equals mass of statue divided by the density of the gold. Okay, it's made of pure gold. So we get this one, right? And we substitute this thing into this expression, right? Yes. Into T1, right? T1 is going to be, because W is mg, we write down mg, m of the statue, m statue times C, right? Minus B, right? B is the product of this term, right? Which is rho H, it's rho of SW sea water
And V of state 2 is this one. M state 2 divided by rho gold is this one. M state 2 divided by rho of gold times G, right? And you could see the common factor right here. The common factors are M state 2, the gravitational acceleration on it, right? M state 2 gravitational acceleration on it. You have M state 2 times G and 1 minus rho of salt water by rho of gold. All right, now let's substitute everything. This one is 15, this one is 9.8, this one is 1, and minus salt water is 1.0103 times 10 to 3. Rho gold is, density of the gold is 19.3 times 10 raised to 3, right? You put this one into the calculator, you would get the result, which is 139.15. It's 139.15 Newton, and that's it for the first sub problem. Okay, I want to finish the lecture right now. Okay, that's the first answer to this question. Actually, there is another situation. Sorry. นะครับเราก็จบเลคเชอร์ภายในวันของวันนี้นะครับเท่ากับห้อง04เป๊ะนะครับโอเค we need to finish the lecture right now. Okay, see you on Friday. There is no homework. Okay, see you พบกันวันศุกร์ if you have any questions just let me know. Okay, if not then we're gonna leave our lecture right now. Okay, see you on Friday. สวัสดีครับบ๊ายบายครับ this